have some view. I want to share some view of from my research, and I like to listen to your opinion. Okay, I find one problem is the very first level of a problem about physics. So we have so many problems with understanding physics because I believe so we have something fundamentally problem. So the first one is about understanding of electricity. The current textbook defined electricity as flow of charge, or further to say, flow of negative charged electron. Is that correct? The current definition of electricity?
Sure, that's usually how we describe it. Absolutely, yeah.
Yes, but I believe that's the problem.
Okay, tell me why.
Yes, good. You keep questioning because I believe there is no any single particle like electrons traveler called a translational traveling on the wire, on the solid wire conductor anywhere. It's a vibration. There is no physical translation motion. So that's number one. And now the second question. So why we get this one wrong? I believe.
Why we what?
Why do we get it wrong?
We get electricity wrong. Because we think about it, there's a particle traveling, but I find that there's no particle traveling. It's all about the vibration. Okay, so now the next question, deeper question is, how did we get the electricity wrong as electricity, like a flow of particles traveling at 70% of the speed of light? So that becomes now the problem with quantum mechanics atomic model. I know you are expert, you taught about this one, and I want to challenging the current quantum mechanics model. So that model initially says, nucleus surrounded or where's the orbital motion of electron in orbital motion. So that orbital motion electron, like in the outer layer, create a valence, electron kind of free flow. So that causes electricity. What I find that the problem with this model is there are no any particle do orbital motion whatsoever. I believe you taught quantum mechanics that originally Bohr's model talking about have orbits, electron, and then eventually evolved to the electron cloud model, right? So that basically says that there are no particle do orbital motion. And that's a second.
Do you mind if I jump in and just give some thoughts?
Anytime.
Yes. So my view, which is mirrored and reflected by, I think, many physicists in the field, is that when you try to use ordinary English language to describe what's happening in the quantum realm, that language is always going to be an approximate description of what's going on. In the end of the day, the most precise description comes from the mathematics. And what we try to do is we try to overlay on the mathematics English sentences in order that we have a deeper intuition for what's going on, because mathematics doesn't give us the same kind of sense of understanding. Now, when it comes to an atom and electrons, we indeed have an equation that comes to us from Erwin Schrödinger, and we can use that equation to describe the properties and behavior of electrons in the vicinity of a nucleus. We can use the math to make predictions for what we should see when that atom is bombarded by light or other particles. And the predictions of the math are indeed borne out by the measurements, which is why this equation triumphed in 1927 over all others, and that's why this equation has stuck with us for almost 100 years. Now, you're right. When we try to interpret that equation in terms of particles and waves, the description can feel at odds with a rigorous description of the reality. Sometimes we use the language of particles. I mean, when an electron bangs into a detector screen and leaves a single little dot, that little dot looks like a particle, and that's why we feel justified in using that language in that situation. When, however, we use an electron to pass through the so-called double slit experiment, the famous of all quantum experiments, then it has a more wave-like behavior, and that's why we use that language in that situation. So when you say there's no such thing as a particle, what I would say is a particle description is useful when you are undertaking certain kinds of measurements, and a wave, or as you said in your description before, a vibration description is more useful in other situations. You have to avail yourself of both of them if you want to have a full description, but at the bottom of it all is the mathematics.
Okay, so I want to go down with along this line. So in your mind, what is an electron?
Well, an electron is a quantum mechanical entity that is described by a very particular equation. It's that Schrodinger equation that I described a moment ago. And in certain situations, I can describe that electron as if it were a particle. And in other situations, I need to describe it as if it were a wave. And I use the phrase as if it were with a degree of forethought, because that's English. That's not the precise language that will allow us to have a rigorous description. So if you ask me what an electron is, and I want to be rigorous in my answer, it is a quantum mechanical wave governed by the Schrodinger equation, and that truly is the description that we can give of an electron.
Okay, so now another question about the electron. Does the electron carry only negative charge?
Yes, it does.
Okay, so that's the problem. When I studied, I find out that this may be the deepest problem. And once we answer this question, probably we can solve the mystery of the universe. Okay, so let's imagine, okay, if you have an electron, and the electron have a mass, so it must have a size. Is that right? So that means...
Not necessarily. So, again, you're using ideas that us from everyday experience. What does size mean when you're in a realm that's so far from experience? It's hard to know whether the very notion of size even is relevant when you're talking about matter at its most fundamental level.
Yes. Good. So let's just talk about the mass. That's the point, the mass. So what happens if you split the mass to two halves? So do the two halves of electron carry negative mass? Do they carry that? Do they carry opposite?
See, we believe an electron may be a fundamental particle, which would mean that it can't be split in half. And certainly there's no observation or experiment that's ever been undertaken that suggests that the electron can be divided in two. So it might be an interesting thought experiment to imagine cutting an electron in half, but it's not an experiment that's relevant to the world as we know it.
Let's do thought experiment. If we put the mass, electron has a mass, we split the mass to two halves. Do they carry negative charge for each half?
Again, one of the deep lessons of Niels Bohr, who was one of the founding fathers of quantum mechanics, was that if you ask questions that are not actually realizable in reality, you find yourself encountering answers that are paradoxical. So he cautioned us nearly 100 years ago to only consider thought experiments that could, in principle, be realized in the external world. And that's really important. That lesson's really important because if you allow yourself to imagine things that can't actually happen, then you can encounter results that will be puzzling.
Okay. I just, because of time constraint, I just share my view on what electron is. Electron is just a little magnetic particle. It has both north and south pole. The so-called electric charge actually just magnetic field.
Well, it's an interesting idea.
Thank you for making that. So you know this is different, right? Thank you for that comment. Because of that, so we can use electron to answer one of the questions I heard from your conversation with Joe. What is it?
Joe Rogan?
Joe Rogan's about whether electron has consciousness and the proton have consciousness or not. Because if they don't have a consciousness, how could the electron and the proton form the atoms, and then atoms form molecules, and forms all the cells, and have a conscious human being? So what I think the consciousness of electron is the electron's magnetic field. So if you think that way, so that field includes the proton. Proton also is a magnetic particle, has both north and south pole. So that's how a nucleus, the light, we call the proton, can form a nucleus called a like charge. They are not repel. Actually, like charge attracts.
Let's take a quick commercial break. We're talking with Dr. Brian Greene, author of Until the End of Time. We're exploring some of the questions about mind, matter, and our universe. We'll be right back in just a moment. Welcome back to A Neighbor's Choice. I'm David Gronowski, and we're doing our Science and You show. We're here with Brian Greene. He's the world-renowned physicist, best-selling author of The Elegant Universe and the new book, Until the End of Time, Mind, Matter, and Our Search for Meaning in an Evolving Universe. Dr. Yu, any final questions?
Yes, I want to finish my thoughts, let Brian to comment. So in my research, I found that the fundamental particle in the universe is only one. Magnetic particles, electron and proton and neutron, all the composition of these magnetic particles. So that's why I say we do not need, I try to unify all the four fundamental forces. Number one, we do not need strong force because the proton itself are magnetic particles. So that's why two protons, so-called like charge particle, they can combine magnetically attract naturally because they are magnetic.
Dr. Yu, do you mind if I jump in?
Okay, you go ahead. Go ahead.
Words?
Yes.
Yeah, so I think it's really important for the listeners to know that when it comes to the fundamental particles that make up matter in the world around us, the electrons, the quarks, the protons, neutrons, and when it comes to the fundamental forces such as the electric, the magnetic, the nuclear forces, the strong nuclear forces, we understand these qualities of reality with unrelenting precision. We understand these qualities of reality with the ability to make astoundingly precise predictions for how these particles and how these forces behave. So any thought that we need to revise or revamp the so-called standard model of particle physics is just not supported by observation or experiment. So it's fine to be skeptical. It's fine to pursue other ideas, but I kind of just need the audience to know that when it comes to the fundamental forces, the strong, the weak, the electromagnetic forces, and when it comes to the particles that make up matter in the world around us, we understand these qualities of the world with fantastic accuracy.
Thank you, Dr. Brian Greene, for your time. Please check out his new book, Until the End of Time. It's a great book. Thanks again for joining us, Dr. Greene.